Hello and welcome back to Educator.com and welcome back to physical chemistry. So we've been talking about energy and we did a bunch of problems concerning energy. Today we're going to talk about our next most important state property, which is entropy. So let's jump right on in. Okay, so before we actually begin our discussion of entropy, there are a couple of quantities that I wanted to introduce mathematically, and then from there we'll begin our discussion of entropy. These quantities tend to come up on a regular basis, so I just wanted to introduce them here. So the first one is something called the coefficient of thermal expansion. Let's go ahead and stick with black, that's okay. So the coefficient of thermal expansion. And I'm going to put in here, in parentheses, isobaric, because this is done under constant pressure. So we designate it with the letter alpha, and it is equal to 1 over v times the partial derivative of v with respect to t at constant pressure. So I'm going to introduce them and then I'll go ahead and discuss what each one is individually. The other one is called the coefficient of compressibility. So the coefficient of compressibility. And this one, this one is isothermal. So you'll sometimes hear this one referred to as the coefficient of isothermal compressibility. It doesn't really matter. So coefficient of thermal expansion, coefficient of compressibility. And this one we designate with the Greek letter kappa. K. Let's make this look a little bit more like a K here. Kappa, and it is equal to 1 over v, the partial derivative of the volume with respect to a change in pressure under conditions of constant temperature. Okay, so let's go ahead and define what these are. So alpha, the coefficient of thermal expansion. So alpha is the relative increase, the important word here being relative. It's the relative increase in volume per unit increase in temperature. Per unit increase in temperature. So that's what this partial derivative is. It just says the rate of change of volume with respect to temperature. If I increase the temperature, how is the volume going to increase? That's exactly what this is. This relative part, I'll discuss it a little bit more in a second, but just real quickly, relative means I'm dividing it by the initial volume that I started off with. I know that if I heat something up, in general, when I heat something up, it expands. When I cool it down, it contracts. That's all this is. This dV dt, if I keep the pressure constant, it's just the rate of change of volume with respect to temperature. So it's the relative increase in volume per unit increase in temperature. Kappa is the relative decrease in volume, relative decrease in volume per unit increase in temperature. Now, if I increase the temperature, if I keep the, unit increase in pressure. The denominator is actually pressure. Now, this says if I keep this is the change in volume with respect to pressure. As I change the pressure, how does the volume change? Well, if I keep the temperature constant of a system, if I increase the pressure of that system, what has to happen, the volume has to decrease. That's where this negative sign comes from. That's what this is saying. So kappa is a measure of the relative decrease in volume per unit increase in pressure. So now let's go ahead and talk a little bit more about what these are. So for alpha, the partial derivative part, dV dt, at constant P, is a change in volume. not the relative, it's just the straight change in volume per unit change. Per unit change in the temperature. However, we take this rate of change, so we take this and we divide by the volume that we actually start off with. We take this rate of change and divide by let's just go ahead and call it the volume we start with before we make any change, before the change actually begins. Divide by, you know what, I'm just going to call it the initial volume. Just divide by the initial volume. So you start with a certain volume, you heat something up by the initial volume. I think it's better. We don't have to write quite so much. Now, when we take the rate of change and when we divide by the initial volume that we start off with, this is what gives us. So what this does, is tell us what percentage of the original volume, what percentage of the initial volume, V, does the change dV represent? In other words, if I had 10 milliliters of something, and if I heated that up, and now the new volume is 11 milliliters, well, the change is 1 milliliter. It went from 10 to 11, so that's 1. Well, if I divide that 1 by the initial amount that I started off with, which was 10, I get 1/10. So that gives me the percentage, which means the volume increased by 10%. Well, what's nice about this, when we actually divide by the initial amount to get a relative increase instead of just a normal increase, is it eliminates, it doesn't matter how much we start off with. So if I start off with, in this first example that I gave, I had 10 went to 1, that's a 10% increase. Well, instead of 10 milliliters of that particular solution, what if I had 100 milliliters of that solution? Well, that solution, it's the same solution, so it's going to behave the same way. So that 100 milliliters, if I heat it up by the same amount, it's going to go up. Now the change is going to go from 100 to 110 milliliters. Well, now the 10 milliliter change divided by the 100 that I start off with still gives me 10%. So this alpha, this relative increase, the change divided by the amount that I start off with, gives me a percentage change and eliminates the need to worry about how much is actually there. That's why this relative increase is more important, is more valuable information than just the increase.